Well, thank you very much for the invitation, Matthias and Marcus, and the organizers. It's a pleasure to be here. I was actually speaking at Peter Burgess' 60th about these quantum functionals that a few years back here in Konstanz, about these quantum functionals that Tobias, where are you sitting now? Ah, there. Was just mentioning. Yeah, it's a pleasure to be back. I'm very sorry, I can only stay today. So, but I'm here till about 9 o'clock. So if anyone has questions, wants to discuss later, I'm kind of available also if you want to go join for dinner or so, I'm here. Okay, so we can just talk and then at 9 I'll disappear. All right, so I will speak about this, maybe I should write down, let's test this infrastructure. Okay, so the title of my talk is Asymptotic Tensor Rank is characterized by polynomials. And I hope at the end of the talk I have sort of convinced you both that it's true, but also made clear what the title really means in all its gory details. Okay, now I'm struggling with the technology here. This is a joint work with Kuhn Hobrecht. with Harold Neubauer. So I also have to look at my cheat sheet here. Peter Vranger, I know. And Jeroen Zoutam. And you can find it on the archive under number November last year, 15789, and it was at this computer science conference stock 25 this year. All right, so we're going to start, I'm going to start talking about rank, and we're going to work our way forwards. All right. Okay, very good. What's a matrix, right? So here's a matrix. It's an n by n matrix. Okay. Now, I'm working in a field of quantum information science, and in quantum mechanics we've got Hilbert spaces over the complex numbers. So my field, my numbers are always from complex numbers. I can read in the paper that we've been writing that all of the results will also hold over general field F. But please don't ask me any questions about this case, okay, in particular, right? So I was trying and struggling to learn from our first speaker today. Very good. So what is the rank? I'm going to call this matrix, I'm going to call it M, okay? So the rank of M is the minimum R such that I can write this matrix as the outer product of some vectors u1 up to un, right? v1 up to vn. Okay, so it's the minimal. The rank is the minimal R. Okay. And now again, let's see. All right. Okay, very good. Now I prefer to write it in this form from 1 to R, such that I get ui tensor v. And I'm going to use, I'm going to use it up here. Yeah, I'm going to use vi here because I've used them as indices down there as well. Okay, so the rank has the property. One of the properties of the rank is that it's easy to compute by Gauss elimination, and we've all learned how to do it. There is another property this rank has, and it's connected to that, namely the following property. The rank of M is smaller than R if all R plus 1 by R plus 1 minors vanish. Okay? Now, let's decipher this. Okay? A minor is the determinant of a submatrix. Okay? And there are, so this is an n by n matrix. Maybe I just going to put it in here. It's an n by n matrix. And of course, I can do this, for instance. R is, of course, smaller than n. So I could take this matrix here. That's an R plus 1 by R plus 1 matrix, right? So let's look at the case where the matrix is n, right? Now, if I want to say the rank is not full, it's not equal to n, that is just saying setting R to be n minus 1, right? And then there's only one minor, namely one n by n minor, which is the entire matrix. And it means, or I have to take the determinant of that matrix, and we all know that, right? The determinant of the matrix being 0 is equivalent to the rank being n smaller than n minus 1. So this is now a generalization of the statement, and now I made my R a little smaller. So here is an example of a minor, but there are other examples of minors. They don't have to be like submatrices like this. They could be submatrices like this. So you select a few rows, and you select a few columns. And you know, this is like 1 up to R plus 1. And then you also get a matrix, namely the matrix of these numbers. And then that's also one of these submatrices you have to test it on. Okay? So this here, now determinants of such submatrices are functions that are polynomial in the entries of the matrix. Okay? So what we can conclude from this is that statement that rank, namely matrix rank, is characterized by polynomials. Right? So that's maybe the first takeaway, right? So that's the formulation of matrix rank is characterized by polynomials. Now we have to understand what tensor is and what asymptotic tensor rank is. And then we will have the same statement. Okay. Are there any questions? Very good. You're afraid of the recording. Maybe. But I'm not. Okay. Now, it has a consequence. Before we do this, let's look at some funny consequences of it. Namely, one consequence is that the rank is lower semi-continuous. Okay? And I can never remember the definition, so I have to kind of like look this up. Okay? It basically means lower semi-continuous means the rank doesn't jump up. Okay? So in a picture, it means that when you have some entries, okay, and you move the entry somewhere, okay, then what might happen is that your rank jumps down, okay, but it will not go up. So it's not going up here, okay? So it only goes down. All right. It's clear because when I have a polynomial, this is characterized by polynomials that vanish. If a polynomial vanishes and I take like the limit in some direction, and it already vanishes, it will still vanish. And that is why it's a consequence of the statement. So if I have if a rank is or something is characterized by polynomials, I can go to the limit, and that will still be true, right? It's sort of like it's a closed property. Very good. I'm sure you know this all better than me, but at least try to remind you. Now I have to start drawing pictures because tensors are three-dimensional matrices. Of course, all the things that I say, they may also be generalized to higher order tensors, but I have a harder time drawing them. And I already have a hard time drawing those. All right, here is a tensor. Tensors are naturally called T, and they're cubes of numbers. And for simplicity, we'll concern ourselves with n by n by n dimensional ones. And then we can say, what is the tensor rank? Well, you know what the tensor rank is. The tensor rank is just now, and I'm switching notation. No, I'm not switching notation. Ui, Vi, tensor Wi, and I1, and this here is minimal. Okay, so this is my definition of tensor rank. And and the tensor rank is already something happens, namely Gaussian elimination. We don't have it anymore. The tensor rank is NP hard to compute. That's a complexity theoretic notion. It was shown by Hostad some time ago. But maybe what is more sort of like algebraic, let's see. What's more algebraic is that the first thing that fails, it's not semi-continuous, okay? And this immediately, by my explanation why this is semi-continuous, will imply that tensor rank is not characterized by polynomials, okay? So, tensor rank is not, I guess, lower. It's also not upper semi-continuous, but that you can figure out yourself. It's not so interesting. It's not lower semi-continuous. Okay, and thus not. Okay, so you want to know why. Who knows already why? Who's got an example in mind immediately? Like raise your hand. Okay, very good. Most of you don't know why. We've actually, yeah?
I had a guess, but
yeah, go ahead.
I was going to say that, so like, in like the Zariski topology,
Yes.
Like a generic matrix has maximal rank.
Yes.
So this is not true for
Yeah.
generic tensor.
Yeah, we're going to try to stay more down to earth, but that's okay. It's a valid reason, I guess. But so actually, our first speaker today mentioned this so-called W state. It's actually a notation from quantum information theory. I think you can even do it like if you like a Waring rank for polynomials. You know, in quantum information, there's called the W state. I think, you know, if people like to think about polynomials as x, y, y. These are all the things where the border rank of the W, or the border rank of the W is 2, and the rank of the W is 3, and so on. Sorry, border rank is 2. Okay, but I think it's so elementary that you should know this example. Okay, and I don't know if that example probably doesn't work over characteristic 2, but I don't care. Okay, here it is. Okay, what's the W in my language? Actually, not quite my language, but E0 tensor E0 tensor E1 plus E0 tensor E1 tensor E0 plus E1 tensor E0 tensor E0. Actually, the W was sitting in my office the other day. It's apparently named after Wolfgang Dürr, the first name, from Innsbruck, actually, one of our second speakers from. Okay, so the rank, right, is like it's obviously written, it's obviously smaller than 3, because I wrote it down in 3 components. And if you're bored during my talk, you can try to prove it. The so-called substitution method shows you fairly easily that it's equal to 3. So you can't reduce the number of copies here. But the border rank is 2. That means I have to present to you a approximation, or like I have to exhibit this W as a limit of 2 rank 1 tensors. And the construction goes like this. You pick an, you think of either epsilon as a formal variable or some small number, like I like to do, and then you're writing the vector E0 plus epsilon E1, and you tensor this to the 3, right? 3 times, and then you, okay, so then you're like, hey, let me binomial expand this, right? So the first component is E0 tensor E0 tensor E0 plus epsilon E0 tensor E0 tensor E1, right? Plus, and then you have the permutations. So that's your W plus E0 tensor E1 tensor E1 with epsilon square, right? And then you also have the epsilon cubed term for E1, E1, E1. Okay, so now, suggestively, I left some space. Now you're going to subtract E0 tensor, E0 tensor, E0. Okay, you subtract it here as well. Let me do it like this, E0 tensor, E0. Then you're going to notice, that this and this cross out. Actually, what they say in Danish is like they go out with each other, like they have a date. So the two have a date, and so here you got your. So now you take the whole equation, right? And you now, because this epsilon was positive, you can divide by it, right? And when you divide by it, what happens? It goes away here, and here it it's like this, okay? So now you see that this here is, the left-hand side is manifestly a tensor rank 2 tensor. On the right-hand side, you got W, and if you shoot epsilon to 0, right, the correction goes linearly to 0. So this is a tensor, and I think my geometer colleagues here would even draw a picture. You know, and they would say this secant here goes to this tangent, and somehow the W lies here. I'm not sure, but I think Alessandro maybe approves or not. So this guy here, I moved down there. Okay, very good. So now you see what happens is exactly, for tensor rank, exactly this terrible thing happens, right? You take the epsilon to 0, and the rank jumps from 2 to 3. Boom. Yeah? Because it's 2, and then in the limit, bang, it's 3. So it's not semi-continuous, it's not characterized by polynomials. Okay, very good. Okay, this was sort of, how am I doing? Any questions? No. Okay, we shift gears. Now we need to understand how to do things asymptotically. Okay. So single tensor is not enough anymore because we understand now everything. Like we have to, the word asymptotic is going to rescue this now. Okay. And how is it going to rescue it? So with this Kronecker product, before there was already the question at some point, Yes, it's the Kronecker product. Okay, so I'm going to define the Kronecker product. So for matrices, if I take a matrix M1 and I tensor it with some other matrix M2, what I mean by this tensoring is that I'm going to take M1, right, and I'm writing it as M11 up to M1n and Mn1 up to Mnn, and then I'm just putting as the entry here another matrix. So I put this matrix M2 everywhere. Okay, so it's now an n square by n square matrix. It's kind of like a block matrix, you can. All right, but it's still a matrix. Okay. So that's like the Kronecker product. Personally, I actually like better to use this symbol, but I think since we don't need any other tensor product, we're going to use this. All right. So interestingly, the rank, the matrix rank, is multiplicative under this notion of product. And there are two sides to inequality. The first is an inequality this direction, and the inequality this direction is kind of like trivial. It's by definition, and has to do with, now I have this like a bigger object, and my rank is defined as a minimization. So it's easy to see that if I have a rank decomposition for this matrix M1 and a rank decomposition for M2, that also gives me a rank decomposition, for R times S, gives me a rank decomposition for this bigger matrix. Okay, that's an exercise. It follows directly from the definition. The other direction follows from the fact that you have the singular value decomposition for matrices. So essentially, you can take isometries or unitaries in my case, and you can conjugate, or like from one side and from the other side, and you can make this matrix diagonal. And that means, and if you think about this here, if I take M1 and M2 diagonal, then I get the diagonal, and of course, if I count now what is the rank of this matrix, I just see it's the product. Okay? So I need this notion of diagonalization for singular value decomposition for being able to do that. And in the case for tensors, so maybe we go, I guess I can just do this part still here. So if in the case of tensors, how does this Kronecker product work? The Kronecker product works essentially by now taking, how do I? So if I'm interested in T1 tensor T2, what do? I look at all the entries of my T1, okay? So here is like T111 up to T11n and so on. And then next to it, I put this T2. Okay? So my tensor becomes this way like an n square by n square by n square tensor. That's again somehow a block tensor. Right? And the same reasoning. So it's again, right, a tensor of order 3, so a three-dimensional object stays a three-dimensional object. Now, if you look at the rank of this, of course, by the same reasoning, the rank will be submultiplicative. Okay, but we know there is no singular value decomposition for tensors, so maybe something goes wrong the other direction, and it does go wrong. Okay, so sometimes it's strict. And who came up with the first example? I don't know. Certainly the first example, interesting example that I know is tensor that we've just seen in Tobias's talk. Is there an earlier example people have figured out? Does anyone know? Actually, very interesting. Maybe I knew once, but maybe I forgot. So how do I display Strassen's rank 7 decomposition in this notion? Does anyone know? Why does Strassen's thing just give me this immediately? Okay, so we'll do a small exercise. Okay, so it's a you start with the unit matrix. Right? In this notation, that's the unit matrix. Okay? Now you embed the unit matrix into a tensor. Okay? It's like if you think about it this way, you just put it, let's say, in the first, you put behind, you put zeros everywhere, and then here you put your unit matrix. Okay? I don't know how to do this now. I hope you understand. So here you put your unit matrix in the first slice, and then in the behind slice, you put, this is your behind slice, and this is your front slice. You put the unit matrix, okay? So that's the tensor T1. Okay, there are obviously 3 ways of doing that, right? So we call them T2, and we call them T3. Okay, so you can put the E1, so, the other way, it's like you put it on the different slicing or on that slice, right? So there are 3 ways of doing that. And if you consider T1 tensor T2 tensor T3, that is my favorite tensor. It's this matrix multiplication tensor. All right, the 2x2 matrix multiplication tensor. In some notation, people like to write it like that. I don't know, what did you write some notation for it? MM2. MM2. Okay, it's MM2 that was in the talk before. Okay. Now, this is MM2, and you listen carefully, that MM2, the rank of MM2 was shown by Strassen to be smaller than 7. Okay? But the product, right, if this was multiplicative, then the rank of them would be, obviously the rank and also tensor rank of this tensor here is 2, right? Then it would be 2 times 2 times 2 is 8. So at some point when you take the product from the first 2 with the third one, it has to drop. Okay? So that's the Strassen example. Yeah. I think it's a very nice example. Right. This motivates us to make motivated Strassen to make a leap of faith and say, hey, maybe we should amortize, regularize, asymptotize this rank. Okay? So we're going to make a definition, and we're going to say, let us look at this function. Okay? You might say that's really, and then Strassen, of course, showed that this exponent was, right? The tensor rank, if it was multiplicative, right, it would grow like R to the n, okay? So now you ask, basically, you ask what is the R asymptotically, okay? Personally, and I think also Tobias, preferred to look at log R of t, okay, which then is the limit of 1 over n log R of t tensor n, okay? But it's a matter of taste, and again, if you take Mn2, this is called, see if you can do chorus, omega. That was omega, okay? Very good. That's omega, okay? So that's omega. And omega is this number between 2 and 3. We don't know what it is, okay? Very good. Okay, so now you know what we're after, okay? And now you can say, hey, now I understand the statement of the title. the asymptotic tensor rank, namely this thing here, is characterized by polynomials, and also it is semi-continuous. So it does not do these things like jumping up. Okay, so that's basically the result. In the remaining maybe 20 minutes, I think, or 25 even. I was a bit late because...
25. Yeah.
25. I will try to give you full proof. Okay, but please ask questions. This is going to come down, this is going to go up. It's kind of surprising that you can rescue this, no? This limit.
I have a question. So, what consult 33?
Yes.
What the dimension of this?
Ah, very good. So it's so if you can think of this, the way I presented it now was like as a 2 by 2 by 2 tensor, right? And then it will result in a 8 by 8 by 8 tensor, I think, if I do it this way. So really, you have this 8 by 8 by 8 tensor, which is equivalent. It's like to Strassen's tensor, which you would think of in 4 by 4 by 4. The alternative is that you start defining, but it's equivalent. It's just like, basically there are some places where it's 0, this tensor. Okay, it's just like hanging out in some 4 by 4 by 4 corner of this 8 by 8 by 8 thing. An alternative would be to define all of these tensor product notions here for matrices and tensors not of the same size, not n by n by n, but like n1 times n2 times n3. And if you do that, you could think of this matrix really as a matrix, namely like the matrix 2 in format 2, 2, 1. And then the other is in format 2, 1, 2, and the third one is in format 1, 2, 2. And then you put them together and you directly get it in format 4, 4, 4. But all of these notions here are invariant under embedding them in like other spaces. So I will just ignore this. You can formally also make this formal. You can say, I define a tensor to be the equivalence class of tensors under re-embedding into larger tensor spaces. So that would actually be a better way of doing it. That's also how Strassen does it and how it was implicitly done in Tobias' talk. So there actually you don't fix the ambient space. For us now, for this talk, actually it's fine to fix the ambient space to some format, and we're just going to fix it, and then we're going to look at the tensors there, and everything will be fine. So just think in a fixed format, playing in n and n, and playing the game in n and n. All right. Okay. Yeah, so maybe I should say one more thing, and so I mentioned Strassen's theorem, right? That omega is equal to this rank of the matrix multiplication tensor. There is a conjecture which is kind of en vogue these days, and it's also due to Strassen, and Matthias is working on it, and I've been looking at it. It's the so-called asymptotic rank conjecture. Asymptotic rank conjecture by Strassen, which will say that R of t is smaller than n. Tilde for n by n by n tensors. And which immediately would imply that like omega is 2, for instance. But we don't know if it's true. But we can ask more generally, which properties does this asymptotic rank have? And like one of the properties I wrote down. But you can ask more generally, what properties does it have? And then you can try. And maybe you can first start thinking like, hey, which properties does rank have, right? And And then you're like, oh, rank is an integer, right? It's defined to be an integer. Rank is an integer. If Strassen's asymptotic rank conjecture was true, asymptotic rank would also be an integer. Right? Because like, there's a notion concise, this inequality you can kind of like forget if you have like not padded by 0 then. So, so asymptotic rank and then the next question you could ask, okay, so I don't know if asymptotic rank are integers, but you could say like, hey, what numbers can they be? Can they be irrational? Can they be, I don't know what, can there be continuous stretches of those numbers? So you can really ask yourself like, hey, here are all the possible values, okay? So all the possible values of rank. Well, by definition, it's going to start at 1, okay? But then what? Right? And so in the past years, people started playing with this. Is there a value between 1 and 2? I think the answer is no. No, there is a value. No, maybe there's not. So you can sort of ask yourself, what are the possible values? And we don't know. The only thing we know for sure that all the integers are contained, right? Because matrices are. Okay, and now I'm going to tell you some things about this. We will have some consequence for this. Okay, so let me formulate this theorem now in that we have. And for that, I'm going to define I'm going to define a set of tensors. But think really of n by n by n fixed, okay? Like you have a vector space Cn, like V vector space Cn, Cn, Cn. It just makes life easier. Just in your head, it makes it easier, okay? Fix a number R, and look at all the T's in this format where the asymptotic rank is smaller than R. Okay? And now the statement of our theorem is that this set is Zariski closed. Zariski closed means precisely, by definition, there is a set of polynomials that carve out this set. Okay? I.e., there exists some set of polynomials, pi, polynomials, in the entries of T, such that T, well, maybe I should give this set a name. Maybe, not S. I don't know what we call it. I don't think we have a name for it. X, R, okay? Such that T is in XR if and only if for all I, Pi of T vanishes. Okay? Well, it's a very kind of down-to-earth thing. There is a set of polynomial, a finite set of polynomial, finite list of polynomials, Pi, in the entries, polynomials in entries of T, such that, if they all vanish, then T is in there. If one doesn't vanish, then T is not in there. Okay? Very kind of down to earth. Of course, this Zariski closure implies, or over C, which is my favorite case, it's like the Euclidean closure. Right? Over C, it's all equivalent, and that is why this W thing kind of also fits nicely into the pictures. You can draw some pictures. All right. And then if you have this theorem, right, it implies, now it's lower semi-continuous. We've talked about that. And it implies this other thing. And I'm not so good with that, but I'm going to try to tell you. It means that the values, so I said the integers are there, but it also says that the values that are there, they're well ordered. Okay, there is a technical notion of what it means for a set of numbers to be well ordered. And what it means is that there are no accumulation points from above. Okay, I think at least that's the way. So what can happen? So here, those we have. What can happen now is that there is some value. Maybe there is some value omega. okay, who lies between 2 and 3. What could happen is that you have some values where it accumulates towards omega. Okay, but for sure, I think it's super funny. There is a gap above omega. Okay, so there is some epsilon bigger than 0, such that there is nothing between omega and omega plus epsilon. Okay, so we don't know what omega is, but for sure above omega there's a gap.
R here is an real number.
Sorry?
This lower R in the theorem, the lowercase r, is any real number.
Yes. Any real number. Okay, you choose your real number, and you say, I mean, this is rank is bigger or equal to 1, but any real number, and then you choose this, and then exactly, that's the statement. Yes. So any real number R, and above, so you can choose it here, right, and you know, anywhere, right? It doesn't have to be a value of the asymptotic rank, but you can say what are the possible, right? It could be like a value that's above omega you can choose, and then the set doesn't get bigger, right? So if you set R equal to omega, for instance, you get some set, and if you now choose an R that's a little bit bigger than, you know, a little bit bigger than omega, then the set will not change. That's kind of what it says. Right. Okay. No, I'm not sure how much. Yeah, so let me try to give you at least some proof ideas. So there is I want to do a reformulation, and I think you can define the asymptotic rank of a set of tensors. So still we have our space. So I'm taking now a set of tensors, and I define the asymptotic rank to be a supremum over all t in the set of tensors. And then, in the set of tensors, T. Okay, so imagine I give you some set of tensors, I take the largest value in it, and I call this R tilde of the set. Okay, it's like an extension of that thing. That's the definition. And now there's a theorem, and the theorem it's equivalent to this other theorem, is that that this notion of for this set, it's the same. So, and I think you can believe me. So if I take the largest asymptotic rank in some set A, right, and now it's semi-continuous, right? In the limit, it doesn't jump up. Then in the limit, it will not jump up, so I can take the limit. Okay? So this statement actually is equivalent to this other statement. Okay, and so we're just going to prove that statement. Okay, that's the idea, and we're going to use a very nice idea from Kasky and Michalek. We have a lemma there we're going to use. And then we're going to throw some information theory at this lemma. I'm going to put that lemma here. And so the lemma says, that if you, we first have to understand, we have to define some kind of notion of the nth powers. Okay, it's clear, right? We need to somehow analyze nth powers. Okay. So when I get a set A, I'm defining now the nth powers of the set A. So I'm going to take all the t in my set of tensors and look at the nth powers. And it's like big matrices now. Exponentially much bigger. And then the lemma, that was the definition. The lemma says that if you first close, okay, you look at the closure and then you take the nth powers. This actually is contained in the span of, how do I write this? In the span of an. Yeah. So when you go to the when you go to the nth power, then the closure is contained in there. Okay? Even actually if you put n equal 1, but then it's kind of boring. Okay? Because I give you a bunch of tensors, and then the tensor that sits in the closure is in the span. But like there's lots of stuff in the span, so it's not so interesting. What is interesting is if you like ramp up this power really high, this like n, and then you're saying like, hey, is my tensor in the limit, like the limit tensor to the n, is that contained in the span? Then it gets interesting. Why does it get interesting? It's because that space is very, very small. Okay? So if you take tensor powers, then it has only polynomial size. So the dimension of this an, regardless of what it is smaller than the dimension of the symmetric power of the space itself. And the dimension of the symmetric power grows as a polynomial in n. This was stupid now. I'm very sorry. I should not have called this n. I used n as my dimension before. Maybe we should try to move to big N. Okay? I apologize. That was really not clever. Okay, it's very small, right? Normally, if you think, it's because these tensors are symmetric under interchange. No, the space they live in grows exponentially, but the symmetric subspace grows only polynomial. Okay, so now what you're doing is like is an information theoretic idea we're going to throw on top of this lemma. Okay, in information theory, people call this idea double blocking. Okay, so we're going to do double blocking. Double blocking. Double blocking. Okay, so here's how it works. So you want to analyze, and now of course my n's are totally screwed up the whole time here. So you want to analyze T tensor n, okay? That's the matter of interest here. So you're going to say, hey, I know what to do with T tensor n. And T, of course, you want to, of course, know that in the asymptotic rank doesn't go up. So the T, you're going to choose an A bar, okay? Then you're like, hey, I'm going to take this lemma, and the lemma tells me that what I can do is I can pick some SI, and I pick those SI, I pick them from A. So I take these SI, and they all lie in A, okay? And then I'm taking a sum over them. Maybe I'm taking the sum over them. And how big a sum do I have to take here? Well, the space is small. I only actually need to take polynomially many. Okay? N, big N. Okay? Very small set, very small decomposition into tensors of this other thing. So you see, if you kind of like think that's small, then basically the T tensor n is like some small sum over stuff from this A. So you're almost done. You just have to now say, I need to do double blocking, okay? Because you need to really analyze this and you need to get rid of this sum. So how do you get rid of this sum? You're going to say, hey, I'm going to take that sum and make a double blocking, right? So I take that block and make it bigger. I take many blocks of this. So I'm analyzing this. And then what I'm getting is like, okay, well, it's trivial. So I can do that. It's like I1 tensor n. Okay, first. Yeah, I just do it like stupidly, right? Nothing fancy. Okay, how many do I have? I have m. And the I goes every time polynomial in n. Okay, so I have to be very, very careful with these polynomials the whole time. Okay. Okay, so now we can already start thinking about rank again. Okay, we want to analyze the asymptotic rank of T, which lied in the border. And so I'm going to look at the rank of this thing. So I'm interested in the rank of n times m. Okay, and I'm going to take these n and m to infinity in some way later. Now, certainly, this is a sum over many, many terms, and the rank is certainly smaller than the maximum of those terms times the number of them, okay? How many terms do I have here? Well, in each sum, I have polynomial in n terms, okay? And then I have many sums, so m sums. So the number of terms is poly n to the m, okay? It looks terrible, but let's not worry for now. Then I'm gonna say, hey, let me look at the maximum over all of those terms, okay? And then I'm gonna take the worst of them, okay? So here, n, s, I, m, tensor n. And now, in a minute, there comes a trick. Okay, so there's many, many things, right? M is a really large number. Think of m as very large. M large, very, very large. Much larger than n. Okay, maybe I have to borrow a couple of more minutes. I think I still have 5. Okay, so I will do it in a few minutes. Here we go. Okay, so now, but you see what you notice is there's many, many s's from I1 to IM. But in total, there are only polynomially many choices of them, right? Because the decomposition had only polynomially many choices. So actually, I can reorder them. Did I write the rank of this? No, you should have complained. It says, of course, here rank of this, right? Rank of, then this argument rank 2, right? Rank is sub-additive. That's why this is true. Okay, so now we just do reordering. Right? So most of these terms are the same, really. So it's poly n to the m, and then I can reorder. I can hey, let's take the first one. Let's take S1 tensor. How often does it appear? Certainly n times. And then let's call this M1. Okay, times S2, n times M2. And there's very few terms. It's only polynomial. N times M, and the index is poly n. Okay. Rank of this. Okay. Now, you see, now you're going to there's few terms, right? Very few. So now you're going to say, well, hey, the rank is also submultiplicative. So this is really of S1 tensor n times M1 times, okay? Very good. Right, now you see these m's, they're very large. So you can now choose them. They're very large. So, for most of them, they will be individually very large. Of course, it's the maximum over the different m's, okay? Here, it's like maximum over m1 up to the m such that mi is equal to m. So you have to be a little bit careful, okay? But for most of them, it's going to be very large. So if there is small ones, you have to deal with them separately, but I'm not going to do it now, okay? So, but if they're very large, what happens? Well, then individually, the terms for which is very large, most of them, individually, it will actually approximate its asymptotic value. It's clear, right? It's like the asymptotic, it's like it will converge there. So this will actually be close to the asymptotic rank of this S1 plus some epsilon, okay? And then, of course, right, to some power, what's the power? M1, right? and then you continue. Now all of those, okay, so now we basically have split it up, and you notice that this guy here is an element in A. Okay? There's only a finite number of these guys, they're all in A, and you all know that the asymptotic rank of this is kind of what you're interested in. That's the left-hand side. So all of those here this is smaller than the asymptotic rank of the set A to the power, well, n times, and then it's just the sum of these mi, which is m. Okay, I forgot some epsilon there. So I have to be a little careful. And this fudge factor, which I was wiping under the rug, okay? So now you look at it, and you're like, relax for a second. You look back, what do you have to prove, right? What you have to prove, where's the definition of asymptotic rank? It was gone, okay. So the definition of asymptotic rank, right, is like R tilde of t. In our case now, it's smaller than, right, R of t tensor n times m. And then to the power 1 over nm, okay? And you want to make this tight, okay? So that's your thing. Now you see from this argument here, this is smaller than poly n to the m, but then you raise it, well, okay, R A plus epsilon, I really give you the complete proof here, and m, okay? And then you have this thing here, okay? So you take this and you do 1mm, okay? And then they all go on a date again, okay? This m guy goes with this guy on a date, right? And this guy also goes with this guy on a date. See that? And then also this guy goes with this guy on a date, and this guy kind of becomes 1 over n, okay? Now, then you see, then when you shoot, now you have to do the order, right? You first take the m to infinity, okay? M to infinity, that gets rid of this fudge factor I didn't talk about. Then afterwards, you take the n to infinity. Okay, when you take the n to infinity, this thing here becomes a 1. Okay, and then you take the epsilon to 0, and then this goes. Okay, and then you're done. Boom. Okay. Well, that's it. All right. Open question, still the same open question. Now you have to prove that there is no accumulation points from below, right? Or like, is it still the integers? But, okay. So thanks for your attention.
Thank you very much. So there will be time for discussion afterwards, but maybe some first questions now. Yes, please.
So your result implies that asymptotic tensor rank is lower semi-continuous.
Yes.
Was that known before, and is there like a simpler proof if you just want to know about this?
No, I think it was not known before.
Okay.
At least to our knowledge. And I think it's probably, if you restrict the statement to the Euclidean closure, lower semi-continuity, I would even think it's equivalent to the statement. Maybe not, I don't know. Okay. I don't know how much lower semi-continuity itself would imply. And I don't know of a simpler proof. It's kind of simple, actually. It's not, it's actually, you saw the entire proof. Mm-hmm. I didn't give you the proof of the lemma, but it's also only 3 lines. So. Yes. Yeah. Yeah, it's very simple to show that it's equivalent to this. I just had to cut time. Sorry, that just takes 5 minutes. Yes. Yeah, it's very easy to see it's equivalent. I just had to cut a corner there to make it fit into the time frame.
So do we know the equations when, say, r is small?
You see, if
In
you
some
know the
cases.
equations for r small, I think only like in, certainly we don't know, no, I mean, I don't know. For any case, I think maybe, you know, I think the better question, or the better formulation, I would say, is the question like, you would go via the format, okay? So you would say R in the format I connected. So 2, 2, 2, we know, because it's easy there. And then I think it's already, I don't know about 2, 2, 3, like these asymmetric formats. But if you solve it in 4, 4, 4, then this equivalent to, then you can solve omega is equal to 2 or not. Okay, so, and yeah, that said, if you can solve it for R equals, if you can solve it for R, if you know the equations for R equal to 4, okay, coming to your question, actually, if you know them for R equal to 3, because there is a Koppenstein-Winograd tensor, if you solve this thing here for R equal to 3 in dimension 3, 3, 3, then you also can decide whether omega is 2 or not. So it will not be, probably not be so easy. I mean, we don't know.
But for r equal to 1, these are just rank 1 tensors.
2 is also okay.
Yes.
2 is okay. I have to think a moment, but it'll be fine. And then it like.
So let's thank Matthias once more. And we will close today's session. Thank you.